Hello and welcome to today's Wolfram Institute live stream. Today we have Isaac Ramos. He was a student of mine at the summer school this past summer, and where he did a project implementing Turing machines in vector fields. And here he'll be talking about implementing computation in the form of classic billiards. Isaac, go ahead.
Thank you. First of all, thank you very much for having me here again. I'm really happy to be able to talk about this new paper that we just recently uploaded with Eva Miranda, that is also here. So yeah, basically the idea of this whole talk is to talk a bit about this relationship between dynamics and Turing completeness and being able to compute and have the possibility of embed computations into dynamics in the case of classical billiards, and see what are the consequences of this relationship between computation and between billiards, because actually being able to embed computations into dynamics is going to be very, very strong, and it's going to tell us a lot about these dynamics. But first, let us talk a bit about the things that we're going to talk about in this talk, billiards. So what is a billiard? And in specific, I mean, we all know what is a billiard. We have all played pool. But here we are going to talk about mathematical billiards. So mathematical billiards is an abstraction that basically consists on a point particle, okay, only one particle, that is moving around on a certain domain, okay? So we all know the classical pool table, which is a rectangular table, but we are going to consider also other domains. And basically, we are going to have a particle that is going to move around, bouncing off the walls, having elastic reflections, okay? So here we don't have any type of loss because of friction or anything. Basically, we are considering an ideal world. And why is this important? Because actually, this dynamical system, although it's quite simple, it's a very, very, very powerful. And already Birkhoff, which is one of the fathers of a modern dynamical system, considered that billiards were like a mathematical playground, because all the formal side, all the things that you need to worry about disappear. And the only interesting part that remains is the dynamics. So basically, you can use them to really test the dynamics and to really see what's happening there. So yeah, and actually Birkhoff identified billiards as the cleanest arena for my dynamics. Basically, you only have dynamics, nothing else matters. And actually, the really cool part about this is that even though they are really, really simple, many things appear in billiard. So we know that there are different types of dynamics. For example, we have integrable systems that have a lot of symmetry and it's everything very beautiful, everything it's very tidy. So for example, if we have an elliptic billiard table, you can see that here you have a trajectory. It looks pretty, like it looks like a drawing from somewhere like an expert, but this is just a ball bouncing off the wall. And you can see that it's like everything is very tidy, everything is very perfect. However, if you change the domain and instead of considering an elliptic billiard table, you consider a square with a circle in the middle, you can think, for example, of a pool table in a bar, and here you have a whiskey bottle. So in that case, the ball is doing crazy things. Like you can see here, this is a whole mess, okay? So you can see that this is really wild. Like it's like a playground, depending. You can switch things that really, they are very naive. You just change the geometry of the table, but really wild dynamics appear. So that is what is cool about billiards, that they are really simple, but at the same time, they are really, really, really powerful, okay? So now, this is not only like you can think, okay, you're a mathematician, you love these things because you love abstraction and all these things, but they actually play a really big role in physics as well. First of all, clearly, this idea of bouncing off the wall with elastic reflection is what is doing the light rays when we have mirrors. So that's an immediate connection with physics. But also, you can use these billiard models to model some physical systems that appear in nature. For example, you can think of a gas, with all the particles, a particle colliding with each other. They're basically moving in a straight line, and when they collide, they basically you have an scattering. So that behaves like a billiard. And also, and this is a bit more surprising, if you have if you have bodies moving around in celestial mechanics, there are some regimes which are governed by collisions. They are really close to collisions, and there are these limits that are really, really close to billiards as well. And finally, and this is maybe not so intuitive, when you have a smooth Hamiltonian system, you can see the limit of this smooth Hamiltonian system with a classical potential as a billiard. And we're going to see later how this appears. Okay, so now we already talked about billiards in mathematics, billiards in physics, but what about billiards in computer science? Okay, because we already saw that billiards are very, very powerful. We have integrable, we have chaotic, but can we have even more? Can we have undecidable dynamics? That's another type of dynamics. In the zoo of dynamics, that's another type of dynamics. So that's what the question that Eva and I ask ourselves and say, we should have this. Billiards are really cool. They are really powerful. They should be able also to compute. And we're going to see later why this is very powerful. I'm going to explain that later. But first, let us talk a bit about the relationship between dynamical systems and computer science. So basically, this idea, we can see how this idea started evolving in a paper by Stephen Wolfram from 1984, when he thought about the idea of having what does it mean to have a dynamical system, something that is changing, something physical, compute. Basically, if you have that you can read a computation through the dynamics of the system, it means that that system has to be at least as complex as the computation itself, okay? Because then it doesn't make sense that something less complex is able to simulate something more complex. So basically the idea here is that if you can embed computations into something, that something is already as complex as computation is. And actually computations are quite complex. Okay, we'll see that later. I will explain in more detail what does it mean to be undecidable and all these ideas. But basically the idea that you have to have in mind is that being able to compute makes you kind of unpredictable, kind of very difficult to get your properties. And then all these ideas, actually, the one that brought these ideas down to earth and actually constructed a physical dynamical system with these properties in some sense is Chris Moore, that in 1990 created a really, really powerful construction that basically encoded a Turing machine, which is the abstract model of computations, into the Cantor set. Okay, we'll talk later about the Cantor set, but basically you can think that you have a square and then doing things to that square, changing some blocks of that square, like stretching, moving around, is the same as the process of computation. So that was the first like real interaction that we can think like in the terms that we're going to think now of dynamics and computations. Okay, so now let's give an example. And I think a really cool example is actually the work by all these people that you can see that they are smiling. Well, almost all of them. Angel here is not really smiling, but they are quite happy. So basically, these people launched a program inspired by some ideas by Terence Tao of constructing a fluid computer, or basically embedding these computations into the dynamics of a fluid. And this is actually very powerful. It has a lot of potential. I'm not really going to go into the details about this, but basically, first, Cardona, Miranda, Peralta, Salas, and Presas proved in 2021 with a really cool construction using contact geometry, the ideas of Moore, amazing, that the Euler equations are capable of computing. So basically, the fluid equations without viscosity. And actually, recently, last year, the Soren Deer, Ángel González Prieto, Miranda, and Peralta Salas, adapting these methods and using also techniques for geometry, prove that Navier-Stokes equations are also Turing complete. So that's really cool. But another thing, and actually this is going to be really important for our talk here, is topological Kleene field theory. And you're going to say, what is topological Kleene field theory? Well, definitely all the people that saw my last talk was in the Wolfram Summer School know about this, because I've been talking about this a lot, because I think this is really cool. Because topological Kleene field theories is a unifying frame. It's basically a really cool way of seeing computations through dynamical system. And what's the idea here? Basically, the idea is that I'm going to have here my Cantor set, and kind of the idea here is that I'm going to be able to encode my information in the Cantor set. So basically, the input of my computation is going to be a point here. And then I'm going to have a vector field defined on these pipes, on these tubes, and I'm going to let this point flow through the pipes. And then at some point, or maybe not, but for this case, at some point, it's going to end the computation and it's going to hit here. What is the really cool thing about this? That if I have a Turing machine, a program, an algorithm, the input of that program is going to be represented by a point here. And then once I hit here, this point is going to represent the output of the program. And you can see that different inputs that here are represented by different color correspond to different trajectories, to different computations. So basically, it's like looking at a computation with your eyes. Like you can see like things are moving as they are computing, okay? And it's really cool. And actually, this image is thanks to a simulation that I did. It was what Dugan mentioned at the beginning in the Wolfram Summer School. So this is really important. And we're going to talk about that later, but this is important because it simplifies a lot of things. And this is going to be like the background, the foundations we are going to use to construct our model of billiard system that is capable of computing. But what about billiards? Definitely some people have thought about this before. What have people done with computers and billiards? And actually, the first really cool advancement in this topic was done by Friedkin and Toffoli. And there, they used a many ball system, so it's kind of a billiard, but using a lot of balls to create some logic gates and to create a Turing complete system using a lot of balls, kind of mimicking how we actually compute using currents and electricity, but instead of using currents, using balls. Then Moore, in his paper about the counter set that I just mentioned, he already suggested that all these ideas of having a counter set, moving and everything, a two-dimensional counter set, could be used to prove that billiard system with only one ball are Turing complete in 3 dimensions. And actually, it was realized by this group that in 1994 gave an explicit construction of a Turing complete 3D billiard system. But then everything stopped. Actually, Moore said, okay, we can do it in 3D, but it seems like there should be a threshold, some kind of limit of the dimensionality, because at the end of the day, you are inserting a lot of information in your dynamical system. So he thought maybe 2 dimension is not enough, okay? Because you don't have enough room, you don't have enough information. So he gave the door open, he left the door open to maybe someday try to do something in 2D with fewer degrees of freedom. And actually, this idea of having 2D Turing completeness in a billiard was very recently explored in 2025 by this group of people. But this is kind of tricky because they use 2D billiards, but actually what they do is a pinball machine. Basically, what they are doing are using pinballs with moving walls, like a pinball, like a billiard with moving walls, like a pinball. So they are also encoding some of the information in the speed, in the velocity of the particle. So when they are hitting these moving walls, they are changing the speed. So they are having one dimension, 1 degree of freedom coming from the position of the wall and another degree of freedom from the speed. So that's like a really cool construction. But what we are doing here is completely different in the sense that our theorem states that 2D classical billiards, you have one ball, you define some walls and they don't move. You don't encode anything on the speed, just have the ball are also Turing complete. And what's the idea here? Basically, my idea is, what is a computer? What does an algorithm do? So basically, what they do is, you give me an input and I give you an output. So our input is going to be a point here in some wall. You can think that you have a billiard that maybe, for example, squares a number. So basically, you have here the wall, and then one of these points is going to represent 3. So your input is 3. You shoot, and then start bouncing, blah, 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 and then you hit another point. And what? This point represents 9. So basically, what I'm going to tell you is, okay, give me whatever program you want, whatever algorithm, and I'm going to give you a billiard table that realizes that algorithm inside a billiard, okay? So that sounds really cool, but actually, we need to prove it. And I'm going to talk about the proof because we are mathematicians and we need to show that things work. But first, let's start slowly, okay? Let's review a bit all the things. So the first thing that we need to review is a Turing machine, which is the abstract model of computation. Okay, I wrote here all the blah, 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 all the text, blah, blah, but actually, in order to understand a Turing machine, you can just look at the picture. That is, I think it's really cute. So basically, what is a Turing machine? A Turing machine has 2 things. First, a tape of zeros and one, which is basically the memory of your computer, and then a head. You can think that it's a little robot. So the head, what it's going to do is going to move through the tape and it's going to erase a number, then write another number, then move, then read the number, write another number, blah, blah, blah. But in order to do so, the head needs some instruction, okay? You need to think like a robot. So you have to tell the robot what to do. So we are going to give the head some instructions, and those instructions are called the state. Basically, you can think that you have a book of instructions, and each page is giving you some rules of what to do. So in page 1, state Q1, for example, is telling you, okay, if you read a 0, you have to do this. You have to change the 0 to a 1 and then move right, for example, and then change to state 2, to another page of the book of instructions. Or maybe if you're in page 1 and you read a 1, you see, okay, if you read a 1, leave it as it is, and then move left, and then move to state 3. So basically, what does a Turing machine? How is the computing process works? Basically, a Turing machine does 3 things. First, the Turing machine, it's placed on a digit, and it reads and writes the digit. Basically, it reads, for example, a 1, and then writes a 0. Second, it shifts. It moves to the right or to the left. So our robot is a bit slow. It can only move one place at a time, but that's fine. That's okay. And then third, it changes the state. Okay? So those are the 3 things that a Turing machine does. And basically with that, you are capable of doing everything that a computer can do. And actually, this is the definition of what a computer can do. It's the definition of Turing machine. And basically, the being computable, being able to compute something, is when you are able to implement that in a Turing machine. Okay, but there is a really cool thing about the Turing machine because, this is funny. Like, we all love doing these kind of things. We are all kind of nerds, so we like to see when something is capable of computing. But this actually matters, and this is actually important for many reasons. And why this is the essential property of why this is important is called the halting problem. So basically, you gave the robot some instructions, but there is one very, very important state, one very important page of the book of instruction, which is called the halting state. Basically, the halting state, what is telling the robot is, halt, okay, that's enough, stop the computation, okay? And whatever you have on the tape, just stop, okay? If you think about our model here before, the halting was arriving here at the end. So that's why this is really cool, because it's very visual. But basically, you have a state that is telling you to halt. And then with this definition, Alan Turing started thinking, and he thought, okay, so you have the halting state, but it could be possible that a Turing machine never halts, or maybe it always halts. So those cases are kind of simple. But there are some cases in the middle. There are some cases where you have a Turing machine that, depending on the input, it starts computing and it halts, or maybe it never halts. It continues forever. I give you a very, very silly example. If you have that the state 1 is, if you read a 0, you leave it as it is, and you move right, and you stay in state 1, if you give an input of only consisting of zeros, the Turing machine is going to move forever from one 0 to the other, and it's never going to halt. Okay, that's very simple to see that that is not going to hold. But actually, if I give you a very, very difficult, a very, very complicated Turing machine, it is a really difficult problem to know if it's going to hold or not, because you could use brute force and say, okay, let's run the program and see if it holds. But what if it holds after 1 million steps, or after 10 billion, or after I don't know? You need the number of atoms in the universe of steps. You cannot wait forever. Okay, so that's actually a really hard problem. And Turing thought, okay, it's a hard problem, but can I construct a Turing machine that solves that problem? Because Turing machines are amazing. They can do many things. I mean, I'm talking to you thanks to computer right now. So they're really powerful, but do they solve this problem? And no, actually Turing himself proved that this problem cannot be solved by a computer. You can run the proof and you can tell, okay, if this was possible, I get a contradiction, so this is not possible at all. So that's really, really strong. There is something that a computer cannot do. Never. So this is the important thing, that basically the idea that I want you to get in your mind, if you need to learn something from this talk, is basically that there are things that a computer cannot do. And one of those things is predicting all the other computers. So basically what I'm saying is, if I have something as powerful as a Turing machine that is able to simulate all the Turing machines, another Turing machine cannot predict its behavior. So what's the big deal here? That if I prove that some physical system, some dynamical system, it's capable of computing, that means that I'm not capable of using computer to predict it. That this thing is algorithmically undecidable. So that's why this word undecidable, because you cannot decide what's going to happen with that thing. Because deciding that would mean that you are solving the halting problem. And we already know almost 100 years ago, Turing proved that that's not possible with a computer. So that's the strong thing. That's why we care about these things. So now that we know this, I know I took my time to explain this, but I wanted to make sure that this was correctly understood. Let's talk about this computation of the counter set. So first, a quick reminder, the counter set is a set in the unit interval consisting of, if you take the numbers in base 3, we know that we are working with base 10 usually, or base 2 if you are a computer scientist, but you can also work with base 3. And there you have digits, you can use 0, 1, and 2. So if you take the unit interval and only use 0 and 2, that's the counter set. So basically, the counter set is actually the simplest fractal you can think of. And the powerful thing about the counter set is that you can encode a lot of information, okay? I'm not going to get a lot into the details, but basically, the idea of Moore was, okay, if I have the memory, the tape of my Turing machine, I can divide it in two and encode one part as the horizontal coordinate in a counter set and the other part as the vertical coordinate. And there, using some things that are called generalized shifts, I can transform the process of computation into dynamics on the counter set. Moving around these blocks of the counter set is equivalent to computing. But actually, these movements are somewhat complicated because in this movement, it's encoded itself, not only the change of the tape, but also the change of the state of the head. So it's like we're encoding also the tape and the state. So it's kind of messy and it works, but it's difficult. Okay. But what's the really cool idea about the TKFT? The TKFT, the Topological Kleene Field Theory, says, okay, don't worry about it. We're not going to encode the state. That's too difficult. So what we're going to do is encode in the counter set only the tape, basically your memory. You have to think that in your counter set is where you place your memory, your tape with your digits. And what I'm going to do is I'm going to understand a Turing machine as a graph. Basically, I told you before how in the process of computing, I'm changing from one state to the other. So if I need page 1, maybe if I read a 0, after doing my process, I'm modifying the tape, I'm going to state 2. So that is represented by a graph. If I am in this state and I read a 0, for example, maybe I move to this other state. So the brilliant idea of topological Kleene field theory is, okay, I'm going to take this graph, I'm going to thicken it, and then in each of the nodes that represent the state, I'm going to insert a counter set, a two-dimensional counter set that is going to encode my tape. So my tape is going to be represented by a point here. So each of the transition is going to consist. Okay, if I'm here, depending on where I am on the point of the counter set, that means that my tape is one or the other. So basically, depending if I'm here or here, I'm going to move here, for example. That's the same as reading a 0. Okay, so this is the reading process. Then, as I know that if I read a 0, for example, I change it to a 1, I move the point a bit around. And then I know I also need to shift the tape to the right. So I also move around. And then I transition to another state. So basically, here I can do everything that a Turing machine does: reading and writing, shifting, and changing the state. And what's the cool part about this? That actually to the counter set, you only need to apply the read and write and the shift. They are not very difficult. They are very simple movements. So because the state change is already encoded here in the position. So this is very powerful. And this is actually what we are going to use for billiards. But okay, for billiards, we have a problem because our encoding, remember that our input was encoded on the wall of the billiard. So the information about the tape has to be one dimensional. Okay? You can see that here the dynamics are 3-dimensional and the encoding is 2-dimensional. It's like transferred to the movement. So in our case, our billiard is 2-dimensional, so the encoding has to be 1-dimensional. And that's the tricky part. Okay? That's the whole point of this thing, the difficulty. Because you have to encode all the information into a 1-dimensional counter set. Okay? So you only have 1 point. And what can we do? Before, I told you that what we did was taking the right part of the tape and use that as our X coordinate and the left part as our Y coordinate. Now we only have 1 coordinate. So what can we do? The first naive idea is, okay, I'm going to alternate between right, left, right, left, right, left. So here, basically, what I'm going to do is going to take all my zeros and ones, and I'm going to multiply them by 2. So they are zeros and 2. So I can see them as digits of a counter set. And then I'm going to start. Okay, my first digit is going to be T0, a center. Then I'm going to take this point, this digit, then this one, then this, then this. And that way, I get a point in the counter set. And we can say, we are done. We have encoded a hot tape in the counter set. Yeah, I mean, we did it. But there is one problem here, that we need to read and write, and we need to shift. And what's the problem here? That shifting this thing is horrible. If you shift this thing, because before, when we had the X and the Y coordinates separated, shifting was like very tidy, very perfect, very elegant. But here, take into account that when we shift, all these things move to the right and all these things as well. But as you were alternating two things, everything gets very, very, very messy. Okay? So if you compute what the actual math that implements the shift is this. This is horrible. Okay? If you want to implement this using a billiard, good luck. If you do it, please tell me. I will be amazed. Okay? But this is horrible. So when I thought about this, it was like, Eva, we're not going to make it. This is impossible. And Eva was like, no worries. We can do the 3-dimensional. It's already done, but it's cool because we are going to use topological Kleene Field theories. But I was like, Eva, but we have to do the 2-dimensional. That's the cool part. Like, you don't play 3-dimensional billiards on the bar. You play 2-dimensional billiard. So we start thinking, okay, what should we do? What should we do? What should we do? And then we had an idea. And it was like, okay, let's do a trick. Okay? So basically our trick is going to be before, okay? And this is a tricky part. Okay, so if you were scrolling on your phone, pay attention. So basically, usually our head is always on the 0 position. Okay? So what we did was shifting the tape around and the head was there, still in this plate. Now we are going to do another thing, and actually it makes more sense. We're going to shift the head, okay? So we're going to have two information. The tape, okay? As you can see, like you can imagine a tape on your table, and then the position where the head is. So basically, if I give you a tape T and I tell you that the head is at position 1, so you can imagine that you have this tape, and then the head is here. Okay? So we have all the possibilities are the tape T and the head position K. And what are we going to do? We are going to have XT that is going to represent the tape. Okay? That point, we know that represents the tape. And we are going to create a lot of copies, infinite number of copies of this tape depending on the position of the head. Okay, this is kind of tricky. So what's the idea? The idea is we're going to have, so here on top, we have a counter set. Okay, so we are going to create a copy of that interval, of that counter set for each position of the head. So for example, this copy, so if we bring this interval here, we make it smaller. This copy here is going to represent 0 when the head is at 0 position. So when the tape is T and I'm at 0 position, my point is this one. Now imagine that I at position -1. The head is -1, but the tape is the same. I mean, basically, it's like you have the tape on the table and you just move the head. So what is happening here? That I have the same copy, the same thing, but here in another interval that I'm going to call I-1. And what's the cool part about this? And this is like calculus 1, that if you make these intervals decrease faster enough, you can make the null fit in one unit interval. So basically before, if we wanted to shift the head, horrible. But now if I want to shift, I just need to move this point here to here, this point here to here, this point here to here. So I need to move all of this to the right and all of this to the right. And that's actually, we'll see later, is doable. And it's not that difficult, actually. So that's the idea. I'm going to encode not only the tape, but also the position of the head, okay? So this is, of course, if you have any questions, please feel free to ask me or we can discuss anything you want later after the talk, but
James
if you want
is
to interrupt me.
James is clapping.
Thank you.
It's really
yeah.
clever. I really like that.
Yeah, I think it's really cool because it's like pushing the limits and it's really fun. So yeah, now we know how to encode all the inputs into a one-dimensional billiard, into a one-dimensional interval, sorry. So now we can actually define what we mean by being able to compute with a billiard. Basically, I'm going to have a billiard table and I'm going to encode all my inputs in a wall and all my outputs in another wall. And then if I have certain input, I'm going to shoot perpendicularly, and then it's going to start bouncing, blah, 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 blah. And if it hits an output perpendicularly, I'm going to interpret that as the computation halting. So I got an input and I got an output. I had my program. And actually, this is really cool that because we are using trajectories that are perpendicular to the boundary, once they hit the halting point, they are going to come back and they are going to do the same path backwards, and they are going to become periodic trajectories. So trajectories that come back to the same point with the same speed. So we're going to see this because we had all this text here, but it's kind of confusing. Basically, the idea is I have here my input, I shoot orthogonally, and then plum, 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 my output. Okay? And I'm able to compute it to embed all the inputs because of this encoding of the counter set. It could happen that it doesn't hit a point here ever, or that it doesn't hit this point orthogonally. In that case, we interpret as the Turing machine not halting. Okay? We can get into the details later when we see the explicit construction, because some people, when we explain these things, are confused about these ideas and get a bit. So if later I will explain it in more detail. So now, let's go. Let's go to the main theorem. So the main theorem is two-dimensional classical billiards are Turing complete in the sense that if you give me a Turing machine, I can give you a computational billiard. I can give you a billiard table and the encoding of the input and the output. And what's the idea of the proof? So basically, the idea of the proof is doing the same thing. I'm going to take my graph of the Turing machine and I'm going to thicken it and create a billiard table. I know this looks like a torture machine, but it's a billiard table, a valid billiard table. So we have here some obstacle and everything. But what's the idea here? If I start at Q0 and I go to Q1, so I'm going to start here at my point and I'm going to start bouncing, plan, 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 and then I arrive at Q1. So for example, imagine that I move from Q1 to Q2. If I read a 0, and then I change the 0 by a 1, and I shift right, for example. So how are we going to represent this? I'm going to represent this edge here by this corridor that is going to move from state 1 to state 2. And what I'm going to do is first read, depending on if I get a 0 or a 1, I move left or right. Then here, I'm going to change the 0 to a 1. We're going to explain that later. Then here, I'm going to shift, and then I arrive at the state 2. So I'm here. And then we can continue. If I move to here, representing that I'm reading a 0, so I'm moving through this whole corridor. So basically, the idea that you have to have in your mind is that each of the transition is represented by an edge on the graph, and in this case, is represented by a corridor that is performing all the computation steps. Basically, it's reading, writing, and shifting. And at the same time, it's moving from one state to the other. And then finally, if I really halt, if I get to the final state, I move into this last corridor where my halting states are encoded. So that's the idea of the proof. But we need to do something. The thing that we need to show is that we are capable of doing this read-write operation and shifting operation using billiard balls. So let's start with the easy one, the shift, okay? Why is it the easy one? Because we constructed our whole encoding just to be able to do the shift, okay? So we were lucky. I mean, it would be very sad if we did all this work on doing the encoding and then the shift was also difficult, but no, it's easy. Why? Because we can use a really cool encoding, because I told you, yeah, you make this smaller, but if you are a bit smart when doing this, you can make that this thing here, from here to here, there is a constant that you are making it smaller and smaller, but by the same factor. Basically, in this case, 3. So that means that this interval here is 3 times longer than this one here. Then this one here is 3 times longer than this one. This one is 3 times longer than this one. So I'm making it smaller and smaller by a common factor. The whole expression is this one. It's boring, so it's basically some formulas. But the key idea is that if I want to move from here to here, if I want to go to the smaller ones, I have to make things 3 times smaller. Okay? So basically the shift, if I want to move from here to here, I make 3 times bigger. And if I want to move from here to here, 3 times smaller. And what's really cool about all this, that you already have this in billiards. If you use some parabolas, you know this idea of parabolas, that everything is pointing to the vertex of the parabola. So basically you can use parabolas which have the same vertex, and then you can increment, multiply your rays by 3 or divide it by 3 using these 2 parabolas. So basically all these ones, all the green ones, were these ones that I want to make 3 times bigger to do the shift to the right, are multiplied, and all the blue ones that I want to make it 3 times smaller to make it to the right are getting divided by 3. So that's it. But this is the shift. It's very simple. I mean, compare it if we come back here, horrible. But here, this is very simple, very cool. We all like parabolas, so we are happy about this. Okay, now the real right. Things are getting a bit more complicated here, okay? This was the other moment where we were like, okay, we're not going to get this, but we got it. So here, with the read-write, what's the problem with the read-write? Okay, so usually the read-write, when we have the encoding before, remember that classically with all the works of Moore or even this work on topological Kleene Field theories, we were encoding the tape as a point in the two-dimensional counter set. And we thought that always the head was at the position 0. So what's the cool part about this? The position 0 is the first digit that you encode. So basically, it's telling you in these blocks of the counter set if you're going to the right or to the left in your first choice. So in some sense, it's very broad. Like you are not doing like, it's the first thing that you see, the T0. But now that we are making the tape position change, the thing about this is that maybe if we are in position K, the digit that we are changing is TK. And that TK can be really, really deep into the counter set. Okay? It can encode position, if you are in K, maybe if K equals 10, maybe that goes position 20th in the counter set, because remember that we were alternating. So it's kind of, they're very deep. So it's difficult to get into it. So yeah, it's this idea that I have here, that TK is encoding deep there, okay? Basically, if you have, for example, K equals 2, you have to change this digit, okay? Not changing any of this. This remains the same. You have to change to decide whether this point is a 0 or a 1. So the idea is that the more you get into these intervals, the more the biggest, like the smaller blocks of the counter set you have to look at, okay? Because this is deciding based on blocks of the counter set. So the idea is that basically, instead of having one block that is 0 and one block that is 1, in IK, you have 0, 1, 0, 1, 0, 1, some smaller blocks. So what's our idea? It's okay. I want to separate the zeros and the 1. So if these are my zeros, the blue ones, on top of the blue ones, I'm going to build some straight walls. You can see these straight walls on top of the blue. That I'm going to make the blue go to the left. And then on top of the red ones, that are the ones that are encoding a 1, are going to be of the other slope that are going to make them go to the right. And that way, I can separate them. And the really cool thing about this, and this is actually where the counter set power comes into play, is that these blocks, although here in this picture, it's not like you cannot see really well, but they are quite far away from each other. And actually, the bigger the K, the more far away they are to each other. Even though you get a larger number of alternation, these are separated between them. So basically, I have enough room to construct this wall, like this zigzag that I'm constructing here, but still I have some room to join this zigzag between them in a smooth way. So basically, the idea here is I have constructed the zigzag like a logic gate. So if I have a 0, the blue ones, I get them to the left. And if I have a red one, a 1, I get them to the right. And then if I need to write a 0 or a 1, basically what I do is modifying slightly the slope And that way, I can modify slightly where they are going to end here, and I can change the 0 to a 1. Because remember, the larger k, the digit that we are encoding is smaller. So there is a smaller difference between being a 0 and a 1. So the change to 0 and a 1 is very small, and I can do all this construction. It doesn't matter if it's going to stay like as a 0 or if I'm going to change a 0 to 1. So basically, this is what implements the read-write operation. And with this, we can do it like you can see there in this drawing, like an idea of how the bigger the k, the more red, blue I get. Because the deeper the digit is, the more red, blue I need. But at the end of the day, this curve is going to be smooth. And in the limit, it's going to be continuous because these line segments are going to get smaller, so are going to tend to 0. And it's true that it's not going to be differentiable at the end of the billiard, of the billiard world, but that doesn't really matter because we all the time when we are considering billiards, we are considering billiards as piecewise smooth domains. So we are going to have corners. So we don't really care that this thing is not smooth in the corner. That's okay. Okay. So the proof of the main theorem is basically we put everything together. And here there is something that we kind of hit, and I haven't mentioned, but here you need to use reversible Turing machines. Okay. Basically, this allows you to paste everything again when you are coming to a new state, to paste the one that are coming from a 0 and to a 1 and not having any problem. So you need to use reversible Turing machine. And this is kind of a technical condition. And actually, it doesn't really matter because if you give me any Turing machine, using more states and blah, 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 and it's going to take more longer, but it's okay. I'm going to be able to construct a reversible Turing machine. So this is not really important, but just to mention it, that we need to use reversible Turing machine to be able to prove the main theorem. So now that we are convinced, I hope, that this thing works. So what are the consequences of this theorem? First, I want you to look at this and realize that this encoding not only is fun and we were able to encode everything like the position and the head and everything in 1D, but this didn't really work with billiards. This was kind of like an oracle because if you look at this, all these dynamics of switching like these things to the left and these things to the right with a vector field flow, at least I think it's impossible. So it's like a perfect match between our encoding and the billiards. And that's really important because I think being able to construct such a complex dynamical system, a dynamical system that is Turing complete with so few degrees of freedom is thanks to this perfect match between the encoding and the billiard dynamics that are so powerful, okay? And so flexible. And then we can apply this construction to a universal Turing machine and get that there exists a two-dimensional billiard table that is Turing complete. And finally, using all these ideas of the undecidability of the holding problem and getting the idea that here, you either hold and finish here, or you're wandering around forever, we can conclude that there are some billiard tables for which deciding if a given orbit is periodic or not, that's an undecidable matter. It means that a computer cannot tell if this property is going to hold or not. And that's good. So now, let's go back to the physical application, okay? So we're going to extend all these results about undecidability of billiards to all the physical problems that are modeled thanks to in taking into account billiards, which are basically hard spheres gases, some collision chains in celestial mechanics, and smooth Hamiltonian realization. And basically what it's going to tell us is that even if you're a demo with all the information in the world, you're not going to be able to predict like this what is going to happen in the future because these things are undecidable, and in a finite amount of time, there is no algorithm that can tell these properties apart. So let's start with hard sphere gases. I think this is kind of the more obvious. Basically, you can model a gas like a lot of spheres colliding, and that's basically like a billiard. And the cool part about this is that usually there are some invariant subsystems, like using symmetries and everything, that can be modeled with these planar billiards. So actually, this is a contribution that being able to compute even in a planar billiard tell us that even some invariant subsystems can have some dynamics that are algorithmically undecidable. Then celestial mechanics. So basically, this is kind of similar. You can think that this is a potential where you are going to have some singularities where the particles are colliding. So basically, you have the collision manifold, that is when the 2 points are the same. And In some degenerate approximation, there is some literature about this. You can consider all these movements of the celestial mechanics as billiard collisions. So basically, all our results about undecidability hints that there is also undecidability in celestial mechanics. And the n-body problem, it seems like it should be also undecidable or have some undecidable properties. And this actually also works, and it can also be more realizable through small perturbations that basically is you have the Hamiltonian of the celestial mechanics and you perturb it by a small parameter that can be, for example, the restricted n-body problem or things like that. And there, it's even more clear that you can have this billiard type dynamics when you consider some limits. And finally, and this I think this is really cool, and this is actually an idea by Moore of how to use these dynamics of billiards to get some physical implications, is that you can have a confining potential. So basically, you have a potential like this one. This is completely physical. Physical. For example, you can think the typical particle that is levitating thanks to a magnetic fields, or this plasma that are trapped using electromagnetic, blah, 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 these really cool things. So at the end of the day, you can think of a ball, and here you have a potential. So it's confined due to this potential. So in the limit, this is physically realizable. So it's a smooth potential. We're all happy. In the limit, if we make this U very, very, very sharp, we get an infinite wall potential where basically here we have free motion. And then when we hit this infinite wall, we get back and we have this elastic reflection, okay? Anyone that has ever done, I don't know, quantum mechanics, for example, has solved this problem in quantum mechanics with the one-dimensional infinite wall potential and all these things that physicists love. And I think it's really cool. And actually, it's a billiard, okay? So you have here that also this system can have some undesirable properties. So in conclusion, billiards serve as models of very different dynamical behavior. And in this case, it shows that they are even powerful enough to being able to embed a universal computational device inside of them. And this is not only relevant for the mathematician that is working on his desk, like only thinking about numbers and abstract, but also for the people in the real world, because there are many physical models in the real world that are modeled after billiards. And being able to tell that a billiard is undecidable means that there are intrinsically some reasons that tell us that we cannot predict the behavior of these physical models. So yeah, so that's all. Thank you all for your attention. And of course, if you have any questions, feel free to ask me.
It's great. Can you go back to where you had the squiggles? So you had the wall shape sorted out
This one?
like that. Yeah. Um, so can you elaborate more on this?
Yeah.
For instance, do they need to be round corners, or is this sort of these are piecewise linear functions?
I mean, I can show you actually, I have here a couple extra slides from the appendix of our paper. So
Hmm.
basically what you need is that thing, okay? You need some straight walls, and that's
Hmm.
the only thing you need actually, because at the end of the day, your computation is only here. Like in these blank spaces, there are no computing states. So that we don't
Yeah.
really care about them. But the thing is that this is ugly. So in order to make it a really cool billiard wall, you need to have some kind of a smoothness, some kind of a curve. So as we have here a lot of space, and this is actually up to scale, I think this drawing tells you really how much space there is between these walls. You can use these little curvy things to join one wall to the other. And actually in the appendix, we proved that you can construct all these walls and you have enough space. We have all the computations. You can look them up if you feel brave enough. And then see if that you have enough space and you can actually join with these small curvy curves that do not really matter. Like in the topological Kleene field theory, if someone is familiar with my simulation, there I just simulated the part of the Cantor set because the other part didn't really matter because there was no computation there. So this is the same thing. So here, the things that are between this strict segment, they don't really matter for the computation. So we
Hmm.
just join them with a small curve that we can use a bump function, for example, to join them just to have a proper billiard. So we have actually a billiard table, a curve.
Okay. So
And
the action is at these points. And you just need the slope
Yeah,
at those points to make that. And then the
yeah,
orientation
exactly.
of those things is dictated by the transition function of the Turing machine that you're implementing.
Yeah, exactly. So for example, here, these
Mhm.
blue ones, basically here, I'm not changing this is a 0 to a 0, so I'm not changing anything. But if I want to change the 0 to a 1, instead of having this one, I'm having this one. Okay, you can see that it's slightly changed because
Mhm.
it's like moving from here to here. Okay, so I'm moving from here to here. So it's like if I wanted to change from a 0 to a 1, instead of having this one here, I will have this one. So it's like
Mhm.
a tiny, tiny change. Okay. So by controlling the slope, I can control the change in the digit. So depending on the ik that I'm changing, I move the slope a little bit. That's why I call this alpha k. But actually, in the limit, the change I have to do is so tiny that in the limit they all tend to be pi over 4 when I approach the other line, and that makes sure that the curve is well defined, everything is continuous, and actually smooth outside of the corners, and we're all happy about it.
Isaac, I think that he was also asking about the. This is something that you and I have very deep in ourselves, and maybe we don't explain it so much. Why do this read and write plus the shift give you
Mm.
the Turing machine? If you Because he was
Mm.
asking about the transition function, if you can recover it from this read and write operation. So
Yeah, exactly.
okay.
So yeah, that's actually like the power of the topological Kleene field theory. So basically, the idea here is that I told you before that Turing machine, what it does is read and write, shift, and change the state. But as a main state is represented by the point on the by a location in the billiard table, the only thing I need to do in this transition function is read and write and shift. Already the state change is going to be represented by moving from here to here, for example. So that's why only read and write and shift gives you the Turing completeness. Because the state of the Turing machine, it's already encoded by the position of the table. It's kind of like, for those familiar with topological Kleene field theories, this idea of the pipes, the only thing that I need to implement is the read write, which is moving the counter set to the left or to the right, and the shift. So here it's the same. The read write is changing, is telling me if I have to go to the left or to the right. Basically, it's this idea is if I have a 0, I go to the left. If I have a 1, I go to the right. That's it. And then here, I adjust slightly the slope if I want to write one thing or the other here. And then here I have my parabolas that shift. And then I come back to state 2 and everything, the transition is done. Thank you, Eva.
Perfect.
So do you know that the topology of the billiard table has to be at least as complicated as the topology of the diagram? Is there any result?
Yeah, yeah, exactly. That's a really, really good point. And actually, there is a remark on our paper about this. So right now, as it is, why did we define a computational billiard as we did, like with all the generality? Because maybe someday we have a dream and then we come up with a billiard table that it's capable of computing and with a really simple topology. But as it is right now, the topology of the billiard table is as complicated as the graph because you can see that there is a deformation retract from the billiard table into the graph. So basically, the fundamental group is the same. So yeah, it's actually a pretty cool idea, and we are thinking and we have thought about it that maybe it's even possible to have some kind of connection between the topological complexity of the table or even and these ideas were introduced in the paper of the Topological Kleene Field Theory by González Prieto, Miranda, and Peralta Salas, of this idea of maybe linking the topological complexity of your manifold in that case, or our billiard table in our case, with the topological complexity, with the computational complexity of the Turing machine. So maybe we can even, we using this term, translate from computational complexity to topological complexity. So maybe, I don't know, if we are able to find a billiard table that is capable of implementing a Turing machine, but with a topology simpler than the topology of the Turing machine, maybe it's more efficient in some way. We don't know, but that's definitely a really good question. Thank you for asking, because that's in our paper and we mentioned it, and mainly based on these ideas introduced by topological Kleene field theory. So yeah, the way we have constructed our Turing machine, the topology of the billiard table is the same as the topology of the Turing machine.
maybe I can add something in this direction, that when we initially thought about this topological Kleene field theory, like for instance, a loop in the computation, it's a loop indeed in the topology. So when you have a loop, and this is what made us think that you should always have computational complexity higher. But as Isaac points out, one day maybe we see it in a different way and we can simplify. Our construction gives one inequality in terms of topological complexity and computational complexity. But there could be other ways to arrange this, because the topological Kleene field theory, let's say we are using here the proof that we provided, but there could be other proofs that don't go through this idea of taking this diagram and stretching it out. Though this was perfect for the billiard because it's a very clear and way to depict the process. Indeed, I think that from now on we should just take the billiard to explain topological Kleene field theory, because it's very clean. It's very clean. This is a joke.
Yeah. But Birkhoff already said that the billiards are the cleanest arena for dynamics.
Yeah.
So yes. But yeah.
Yeah,
Thank you
so
very
now
much.
it's cleanest with K. It's the
With
transgressive.
cleanest. Yeah.
Nice.
But yeah, that's actually what I said before about the topological Kleene field theory, that it's a really cool way of visualizing the computation, because you're moving around the states and then you are changing your information.
Yeah.
And another question. So you said that the corners are very important, that otherwise basically the curve would not be, the boundary would not be smooth. So that's something what is somehow interesting, that it somehow interplays with this fact of kind of realizability of the Turing machine, that the boundary has to be kind of has to admit corners, right?
Yeah.
So
Yeah. And actually, I mean, I think, I don't know, maybe you can try to encode it in some way and modify it a bit not to have corners. But at the end of the day, as billiards people, like the people that do billiards like very seriously, they are all happy with corners. Like, I mean, even a classical pool has corners. So it's something very natural to have corners in a billiard table. So in our case, we just left it as it was, but having some singularity on the corner with respect to the differentiability, and everything is fine, because at the end of the day, whenever you are thinking of a billiard, you think of corners. So it's fine. And actually, usually the definition of a billiard, the curve of the boundary of the domain you're considering is usually considered to be piecewise smooth. So that's why it's fine to have some singularities on the corners.
And my last question, if nobody else is having a question. So you said this relation to the collision orbits in the celestial mechanics. So how to see it? So what would be the equivalence of like read write operations and shifts in collision dynamics
Yeah, in that case, the connection is a bit more vague. So basically, the idea here, and maybe later Eva can elaborate a bit more on this, but the idea here is that we know that there are some regimes in celestial mechanics, especially some approximations, that behave as billiards. So our point is more that these results that we have in billiards points and hints towards undecidability in celestial mechanics, that it's a really big open problem right now. And it's not like we are claiming that celestial mechanics or the n-body problem is undecidable, but it tells us that some approximation of it, some regimes of it, can have some undecidability that are inherited as billiards, because we can try to mimic this billiard construction using these regimes, these billiard-like regimes in these physical problems. But it's not like saying literally that we have an embodied problem solution, that it's Turing complete, where we have a shift, a rewrite. That's actually work, as far as I know, work in progress by Miranda, González Prieto, and Peralta Salas.
Very much in progress. So the problem is that we like in this language that Isaac was introducing, we have the shift embedded in natural/dynamics, very nice, but the read and write is very difficult. And indeed, we are thinking how to make it happen. But this would be a first indication that we are in the right direction, thinking that the three-body problem can be undecidable. So to have these models. And coming to the question of Pavel, like I think he was asking, how can you relate this kind of zigzags that you need to have for the read and write in this problem of collision or potential collision of planets? The models that resemble these billiards are related to the scattering maps, okay, connected to collision. So in a way, it's like you have to assume that the collision is produced along having this kind of very complicated topological of the collision set. Of course, from a physical perspective, we are not used to thinking in these terms because we always work with ideal models in which you don't have this kind of ruts or this kind of slopes, right? But it would be possible maybe to give a physical interpretation of the slopes. But well, these models are models that one important thing is that these models are in a time is not infinite where you have these kind of models. These models occurred at a certain time. So from this point of view of undecidability, let's say it's a bit vague because you don't have it for all time, right? So these models are just localized close to collision. So it's more like an indication that that you may have these undecidable events in celestial mechanics, which is really cool, I think, because these are real problems. So it's more like an indication. Again, this is a model, so as a model, it's not perfect. And
Yeah.
then, of course, on the model, the model that we are using, our billiards have not only the topology of the table, but as Isaac is saying, in order to be able to make this encoding compatible with the billiard ball, which is this very nice idea of the encoding of going one side and the other, is that we need to put some kind of geometry on the table. It's not only the topology. And this is what in the physical models is maybe more difficult to conceal. So we should be able to find, for these physical models, a geometrical explanation for this zigzag. But we need to think more about that. It's an
Yeah.
idea.
And yeah, usually, probably in the general embodied problem, I would say that this restriction of having a planar dynamics, maybe you can get away without using planar dynamics, and then you can
Yeah,
use the traditional
yeah,
two-dimensional
exactly.
counter setting, and then you don't need this zigzag or whatever.
Yeah, that's
Because in
the
the
other thing. Very good. Yeah, that's the other thing I wanted to say when you were saying about all this, because this is two-dimensional, and as you said, this is very cool, to simplify and to be minimalist nowadays and not to spend too much money. So we want to be 2D. But already in 3D, it was with the ray tracing ideas that Moore proved that
yeah,
it's Turing complete. So maybe you are right. Maybe if we go to higher dimensions, we don't need to play
and
this
exactly
smaller
celestial
dimension.
mechanics.
Yeah, in the
Yeah,
celestial
exactly.
mechanic
More or
problems.
less the same thing that happens here in the
That's
TKFT, where you have
yeah. And then we need to
two-dimensional
be able
counter
to
sets.
put the polygonal sides, right? The planes.
Yeah. So here, if you do
Yeah.
something similar to this, but with billiard dynamics, you don't really need a zigzag, because the
Yeah.
zigzag is to conceal this really complicated encoding that was constructed only for the 1D encoding. But when you have like a typical counter, two-dimensional counter encoding, the read and write is very, very, very simple. And
Yeah.
actually, if you see into the details of the paper or the simulation, you would see that it's just a linear map and a fine
Yeah.
map. So it's very, very simple. So probably in the celestial mechanic case, at least in the first case, it would be more wise probably to look at the
To
three-dimensional
look at
case.
the 3D
Mhm.
models, at the models that are
So,
higher T. Yeah.
so something like that, the TQFT diagram would be, let's say, realized by some hyperbolic fixed points in the plane of the planar problem, and this would kind of homoclinic heteroclinic chains, they would somehow realize the shifts between the states or something, and right would be the z direction, some oscillation in that or something like that, or
Yes,
something
yes,
like that.
yes, exactly.
Okay.
Yeah, exactly. Yeah. So essentially, the way this topological Kleene field theory, you are computing following the flow of a vector field, which is transverse, in this case, to the borders. So you have this kind of the composition of this spaghetti, you call it. Isaac calls it a spaghetti picture.
Yeah, I
This is
think Duan and I came up with this terminology of all this spaghetti flowing around.
Yes, that's nice. I think that's that's very cool. And if maybe you have here the animation that you can show of
Yeah, let me have a
the
look at it.
topological Kleene field theory, what you did already,
Yeah, so
which is
let me
very
check it.
nice.
I could very real quick. So yeah, and if anyone has any further question, we
I'm
can
sorry.
continue talking. But yeah, I'm going to show the animation because probably this is going to be very instructive for everyone. So let me look at this and try to look for every one of these
So
animations.
we are converting people to topological Kleene field theory.
Yeah.
Yeah, for sure.
Okay.
Isaac, you need
So
to
let me.
share your screen.
Yeah, I was doing that.
Okay. Oh, perfect. Yeah.
Yeah. So basically, it's this idea of like maybe I can do it manually. So basically, here is what is the Turing machine doing? Here, it's reading a 0, which is represented by the left part of the square. So it's going through the left part of the transition, and here this is changing from a 0 to a 1. You can see that this is a really simple movement. It's just changing from the left part of the square to the right part. There is no zigzag whatsoever because here the encoding is helping me. I have a lot of room because I'm in a two-dimensional encoding. And then here, this part represents the shift. And then this one is coming back to state 2. So basically here I have the computation. So instead, for example, here, instead of reading a 0, it's reading a 1. So it's going through the other transition and then continue computing, blah, 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 until it halts. So you can visualize that basically the whole computation process is represented by the particle moving around the graph. So this is actually,
And
if
so,
anyone is
this case, so
curious about this, this is the two-state case. There is another simulation of a three-state Turing machine, and there is even some code written, and I published it in order to that enables anyone to simulate any Turing machine of any number of states, and you can create and simulate anything. So everything is in the Wolfram community page. So if you type Isaac Ramos Wolfram, you can look at it and you can see all the simulation. It's as a community blog post. So you can have around, play with the code and everything, and all the simulations are there. And yeah, so my work in the Wolfram Summer School was doing this for the two-state case and the three-state case for the Turing machine. And afterwards, I completed the simulation to being capable of simulate any Turing machine of any number of states. So yeah, maybe someone else has some question. I can come back to the slides. Or
well, yeah. So I mean, I guess there's a conceptual question. So in 3 dimensions, you have enough room to take a Turing machine with its transition functions and then construct a vector field that'll move, trajectories from Cantor set to Cantor set in a very nice way. So you're moving from tape readings and head positions to different tape readings and head positions using a vector field, a 3-dimensional vector field. And in the 2-dimensional billiards, like you have these trajectories, but individual trajectories can like overlap with each other.
Yeah,
or
exactly.
You might have
so
a trajectory which goes around and like crosses a previous.
That's a really good point, and that's actually one of the powerful thing about the billiards. And actually, you can already see here that here trajectories are crossing each other. Okay, but this is not. And I talked with Eva, and we discussed it. Like the two of us, if you recorded and said, we were like, billiards are amazing. We love billiards. We're like in her office at Turing, and we're like, this is amazing. We love billiards. They are so cool. Because precisely they can do this. Because in a vector field, if I give you a position, you already know what trajectories you need to follow. But here, billiard trajectories can cross. Okay?
Mhm.
And basically, you need the position and the speed. So basically, they can cross. So I think your question was more in the line of how can I make everything fit? But the idea is that I can have a crossing, like if I have two edges of the graph crossing, that's completely allowed. Imagine like you have a cross like a car crossing, okay? The thing is that you only have one ball. So nothing is going to collide with anything. Basically, if two edges are crossing each other, you can have one ball crossing and then maybe later it crosses in the other direction, but nothing is, as long as you fit everything together, there is no problem about that. It's not like in the
Right, right.
fluid case, in the vector field case, where you have only one vector field defining your whole manifold. So you had to make sure like there was no crossing trajectories. But here the trajectories can cross, like you see here. So that's
Mhm.
the actual powerful part of the billiards. So that's in the heart of the billiard dynamics. And that's
Right,
actually
right.
because that's actually why here we don't really care about the graph crossing with each other, like blah, blah. So I don't know. Imagine if I have here, probably I should have a drawing of this for the next talk. Probably I will try to have some drawing of this because I think it's an important point. But basically, if imagine that I have here, I don't know, another edge that goes through here. So I would just need to go through here. I need to take care of everything not colliding with the important parts. But basically, if I have another trajectory crossing through here, there is not going to be any problem because, I mean, it's the balls are not, you only have one ball. It's not going to collide with anything.
Yeah, it's not going to collide with anything. But yeah, again, it might circle back around and cross over a position where it just was. And yeah, so in that case, it's doing dynamics, billiard dynamics, and it's a question like, would it be not possible to ever encode a Turing machine into a two-dimensional vector field?
That's a good question. And actually, that's one thing that I think would be very interesting. Can we do it in a vector field? Can we do it in a solution of the Euler equations? That's another question. I think with this encoding that we have, it's going to be very difficult. Mainly because this zigzag doesn't work with vector fields because you have this crossing.
Right.
That's where when I was saying that the encoding and the billiards dynamics is a perfect match is because of this. Because you can have all this crossing and you're happy with that because billiards are cool. But with vector fields, which are really cool also, but in a different way, you cannot have this. So I think there you need to play, probably you need to play even more with the topology. If you want to have 2D dynamics that are they are undecidable with vector fields. And I think that's really cool. And I have thought a bit about this and probably it's future work. But yeah, and it would be really cool to show, for example, that 2D Euler equations are Turing complete. But then you have to really think about this because you have to make weird things with the topology. Like instead of having this zigzag with the geometry, probably you have to have like different height, even though if you are in 2D, like hold your manifold, I don't know, your surface.
There are things like we can discuss, Isaac, because there are like 1D encodings.
Mm.
That this is more or less the idea we were using with Daniel and Robert in this
Yeah.
article of the Journal Mathématique Pure et Appliquée. And that idea that we were following there is quite compatible with the idea of flowing with the vector field. So maybe we
Yeah,
can,
the GX, no? The
yeah,
the
because
generalized.
there we were using a kind of we were using the idea of just expanding something 1D to 2D by using by just using a kind of product with an interval. So now instead of thinking that this is a product with an interval, we could just try to make it flow with a vector field. So maybe we could try to use this This would be nice.
Yeah,
Let's discuss about
yeah, I
that.
think so.
Yes. I didn't think of that indeed. That's a very good point. Yeah. That's a very good question.
Yeah. I mean, what I'm getting is like 2 dimensions is not capable of having a vector field doing this computation. It's like, if you have a line and you're trying to flow upwards, sort of, but you need like this one over here to like go over there, and this one over there to like go, to cross each other. You can't do it on a plane, right? So there's like a fundamental topological
Yeah, what I thought is that maybe you
constraint
can
there
have
that you can't.
your surface like tear up, like separate,
Yeah.
and then you have like different heights. You're still
Exactly.
like 2D because
Exactly.
the problem with this is that you have like when you are instead of losing differentiability, when you get to the corner, like we have in the T6 you start getting a really messy thing with the different heights and everything. And I think we kind of discussed this with Angel as well.
But for instance, for the paper for what we did with Robert, not the things that we try to do with billiards.
Yeah, no, I know which one you're
The
saying. The
Euler,
one
that
of
construction.
the Euclidean Euler.
Yeah, we
that's
had a
non-compact.
cube, and then we were able to make things smooth. So it was not the same. It's true that there was not vector field, but I think a similar idea could work. Let's try.
I think the key trick there in that construction, that is for anyone interested, is the Euclidean 3D Euler flow, which is Turing complete. If you type something like that, you can look at the paper. There, I think the key part there is that you use the real numbers to encode the Turing machine.
Yeah.
So that's where here, if you do the same idea with the whole real line, you do.
Compact. Yeah. I don't know. There are ideas. We will discuss this. Exactly.
Yeah, maybe we can discuss it in Madrid.
Yes, we can do it together in Madrid if we have time, because we have all these talks. It's quite intense. In the dinner. Official dinner.
I'm sure that if we have enough wine, we'll make it. So yeah, when anyone else has further questions?
This is really exciting.
Thank you. Yeah.
That's my favorite picture. Yeah. I show this to my husband and he says, "This is not you. This is you 25 years ago."
I don't know. I think that ChatGPT did a good job.
Exactly. Yeah, I think so. It took the best part of both of us.
Yeah.
I like that. Writing the 8-ball. It's like, it's a toy where you ask the 8-ball a question and like it'll tell you like the answer. But here it's just like, oh, you just have to see where it goes.
Yeah, exactly.
Yeah. And it's very powerful. Only one ball, that's all you need. So yeah. Well, so then thank you again for having me here and for giving me the opportunity to present the paper. So of course, if anyone has any further question or if anyone is watching the recording, feel free to ask me any question at my email. And yeah, thank you very much for having me here.
Thank you so much, Isaac. Thank you for joining, Eva. We look forward to seeing you in Madrid.
Well, yeah, see you all soon. Well,
bye.
Pavel and Dugan and James, you will be there online maybe at some point.
Yeah, I'll be there.
Okay, it will be good to see you. Great.
Okay, thanks everyone.
See you.
Bye.
Thank you.
Bye.
Bye.